Okay, let's get started. This is the kind of general procedure for system design development. And risk analysis play a kind of gatekeeper role. First is hazard identification. At this stage, we try to identify the hazard that can influence the safety or environment impact or asset damage. Then we set up a kind of design philosophy that should address the hazard identified at this stage. Then we develop kind of skeleton of the system. That skeleton is called process flow diagram. We come up with the kind of configuration of main equipment, compressor, heat exchanger, blah blah blah, and then we carry out process simulation. The main product of process simulation is heat and mass balance. With the heat and mass balance, the equipment designer can design their equipment. For example, the heat exchanger designer needs information about incoming flow rate and temperature pressure and the outgoing pressure, temperature, and flow rate. Based on that information, the heat exchanger designer can develop the detailed features of heat exchangers, number of tubes, and the internal baffles for the heat exchanger. Then we have a physical size of the equipment. With that information on the physical dimension, then we have a kind of layout. And there's another big important task is process and operational philosophy, how to operate the system. Then we can develop the detailed specification for the process control and measurement and sensors. Those kind of informations is included in piping and instrument diagram. And FDS is a functional design specification. It is a detailed description of the control loop and operational set values. Then we have detailed process information and equipment layout. Then we can carry out HAJOP at this stage. HAJOP is a more detailed analysis of the system from the viewpoint of safety. The objectives, main target of HAJOP is safety, not the process efficiency or performance. Okay? HAJOP is aiming at the system safety, not the other things like energy efficiency or economic feasibility. Then we usually correct the design. Then we can carry out the risk assessment and the reliability assessment. If the requirement, if the result of the analysis is not satisfactory, for example, if the estimated system availability is less than the target value, we should change the system design. If the design is minor, we can go back to here. For example, we can change the equipment specification or we can change the process configuration. In many cases, the deviation is too big, then we should change substantially the system backbone. Then that means we have a lot of things to do. So the first early stage of the design is very important in design a complicated system. All the risk analysis and reliability assessment cannot be done all together. There is a kind of procedure. Some risk analysis should be done in advance. Some should be done, can be done only if we have some information about the early studies. So this is kind of procedure we carry out the risk analysis. So the first step is hazard. Then fire risk analysis is very important because it provides the risks concerning the fire, and it provides many important informations to other studies. Then we carry out explosion risk analysis, PFP study, and these are kind of system reliability assessment, serial location, heaps reliability, and the production availability. Then all the studies should be integrated in one report. That report is called QRA, Quantitative Risk Assessment. That's the overall summary of our last class. Today we will go deeper into risk analysis. Today's topic is definitions and characteristics of several risks. As you know, risk is just combination of frequency times consequence is the definition of risk. Okay, but in reality, there can be several consequences. In that case, we need to sum all the risks. Okay, the total risk is the sum of partial risks. So partial risk is the partial frequency multiplied by partial consequence. So we should sum up all the partial risks. Sometimes the frequency can be replaced by probability. So you should be very careful. Okay, sometimes we use frequency. Sometimes we use probability. For example, PFD, probability of failure on demand, can be defined in terms of probability for low demand case, and for high demand case, it was defined by the frequency. So you should be very careful in estimating the risk. And only the same kind of risk can be added. What I mean is that the risk can be on safety, sometimes on asset, or sometimes on environment. So these three factors, these three are called dimensions of risk. So risk has three dimensions. One for fatality, safety. Another, asset. And the third is environment. You may remember this slide. Risk is loss per time. The loss can be death or fatality for safety. It can be monetary terms for asset damage. It can be failure frequency for automobile industries. So you should be careful of the unit dimension of the risk. So fatality or death of the crew is the most important issue. So we don't use the term death. You should always use the term fatality. Okay, I wrote down the term death here, but it's for your understanding. So you should not use the term death. You should always use the term fatality. Accident leads to consequence, and it may have impact on personnel, environment, and the asset. When it comes to personnel, fatality is the most important issue. So the focus of QRA is always on fatality. Injury can be handled, but as you know, fatality is far more important than the injury. So we usually focus on fatality. Second thing is about impairment of major safety function. It may sound a little strange. Okay, what is the meaning of impairment? Impairment is just loss of function. Okay, so so that means failure of a major safety function. Okay, impairment can be interpreted as failure. So, but we usually use this term, impairment. Major safety function is the important facilities that are supposed to protect the safety. For example, in the FPSO, there is a sheltering room. That room is called temporary refuge. The role of the room is to provide sheltering space when there is a big accident like a fire or explosion. So the crew can escape into that room, temporary refuge, to save their life. So impairment of those kind of critical safety facility means that the crew, we may have a lot of loss of crew lives. So this is the indirect way to measure the fatality. And environment is, there are several kinds of environmental risk, but the top priority is environmental damage by crude oil. Gas, natural gas can contaminate the environment, but as you know, gas can disperse into air. Because the the amount of accidental release is not that significant, so the impact on environment caused by the escaped gas is not that significant. Okay, it's a kind of temporary release of the gas. So pollution by natural gas in an accident is not a big issue. Always the crude oil spillage is the most important. Asset, there are two kinds of asset risk. One is material damage. For example, we have a fire, and the some equipment, thermally damaged equipment, for example, a compressor, then we lose the compressor. That means we needed to replace the compressor, paying a lot of money. That is the one issue of asset damage. But the more important one is production loss, delay of production. We have a reservoir, and we produce oil and gas from the reservoir using the offshore installation. So usually one day, for a day, the offshore installation is supposed to produce tens of $millions oil and gas. So stopped operation for one day means several million or tens of $millions. But as you can imagine, a fire accident can cause several months production loss. So production loss is more important than the material damage in many cases. Is it clear to you? Fatality risk. Then the first question is, how can we express the fatality, death of the crew? One is potential loss of life. In short, PLL. PLL is fatality per platform year. Platform year means the number of years for which the platform is operating. So it's not calendar time. It is the operational time. So fatality per the period when the offshore installation is operating. Second is, so this is a kind of inclusive representative. What I mean is that in an FPSO, for 1 year, for 10 years, we have 12 fatalities. Then potential loss of life is just 1.2 per year. Okay, 12 times 10, so 1.2 fatality per year. This is the meaning of potential loss of life, definition of potential loss of life. Personally, this value has has a little meaning. What I mean is that if the installation is big, this value will be big. If the installation is small, this value would be small. So personally, if I were the operator of the FPSO, the important parameter to me is that the probability of death for me, my probability of my death, my fatality, not the kind of PLL. So what I mean is that this value is big or not. This kind of question is sometimes hard to answer. For example, in this FPSO, let's assume that we have 100 people, 100 operators in this FPSO. Then the death, the probability of my death is 1.2 time divided by 100 means this is the probability of my death, because they are, if we assume that all the people had the same probability of death. If there are 300 operators in the FPSO, this value will be lowered by factor of 3. So this number of crew is important. So what I mean is that individual risk is more important to a specific person. So we usually introduce another parameter. Another thing is group risk, and they are kind of alpha and curve. I will explain later. So what I mean is that there are several expressions for fatality. So which expression should be taken has to do with their interest. What is the purpose of our report? For the offshore installation, the owner of this FPSO, maybe potential loss of life is an important indicator. How many people can be killed in our FPSO? That's the question. That's the one of the most important questions. The offshore installation owner should answer. If I were the operator, my primary interest would be the individual risk. Okay. Potential loss of life is the fatality per platform year, and it's a number of fatalities in a period. So usually year. So PLL is the sum of all the possible fatalities. This expression looks complicated, but the implied philosophy is that all the fatality should be summed up. And so all the causes of fatality should be accounted, and from PLL, IL, GL, FN curve can be estimated. So what I mean is that if we have basic information on the fatality of each accident, we can generate all the information, individual risk, group risk, and FN curve. You may remember the event tree. This is the event tree. You may remember this is the leak, okay, leak, and there will be gas detection system here. Gas is detected or not, then fire is detected or not, blowdown system is working or not. This kind of thinking is event tree. Okay, so at the end of the event tree, we have accident. Each branch means one separate accident. If we sum up the probability, we have the frequency of that accident. So that accident may have impact on safety and asset and environmental damage. So this part is prepared to estimate this risk. So, for example, this accident can cause 3 to 5 death or fatality, then or and this accident can cause high asset damage. So we need to define what is high asset damage. They can be maybe $200 million, like this. So what I mean is that when it comes to safety, we need to sum up all the fatality. So the total fatality is we have frequency here, frequency of this accident, and this accident. And we should multiply this one and this one, this one and that one, this one, that one. So this is the meaning of this equation. All the accident and all the fatality concerning the accident should be accounted. So in estimating the potential loss of life, all the fatality of the installation should be summed up. And PLL is intrinsically proportional to the size and the size of the crew of the installation. Can you understand me? The bigger the installation is, the bigger its PLL is. So PLL is just fatality per platform for that installation. So it does not have any information on the size of the installation. If the installation size is big and there are many people, the PLL would be great. Can you understand me? No? What is the fatality of Daejeon per year? Maybe 1,000. That's just what is the PLL of Korea? They should be far greater than that of Daejeon because there are more population in Korea than in Daejeon. That's the weakness of this parameter. This parameter PLL is just the death of the operators or crew for that installation. So the PLL should be proportional to the size of the installation. So that's the reason we should introduce the concept of individual risk. Individual risks are expressed by two terms, two ways. One is FAR, fatal accident rate. Second is AIR, average individual risk. And FAR, fatal accident rate, is we normalize the platform size. In this case, more definitely, FAR is equal to fatality divided by 10 to 8 exposed hours. This is the working hours of all the operators. What I mean is that there are 100 people here. What is working hours per year? They will work 8 hours per day times. This is the working hours of this for these 100 people. This equation is usually applied to onshore installations because some people will leave after working 8 hours. In offshore installations, all the people should be inside the installation. So the calculation, considering the shift. What is the shift? 우리말로 뭐라 그러지? 교대. Considering shift offshore installation is not like the onshore installation. The people, the operator should inside even after working 8 hours. So anyway, we'll cover this concept later. Anyway, this is so 10 to 8 is kind of normalized one. So it can account for the size of the installation or the size of the crew, in strictly speaking. So only exposed hours considered for all workers. What is exposed hours? Exposed to what? Exposed to risk, okay? Exposed to hazard. All the exposed. If the people here inside in living quarter and the living quarter is completely safe, we don't have to count those people. Okay? If the people walking on the deck and they are exposed to risk, the working hours for those people should be accounted. That's the meaning of exposed hours. So let me repeat again. The people stay in the living quarter, sometimes hard to deal. They are completely safe. So we need to think about that later. AIR is sometimes called individual risk. I prefer this term, individual risk, or ILPA, individual risk per annum. I mean the dimension of this risk is death frequency per year. So someone prefer this term because the unit is per annum frequency. Annual risk per person is considered, and we respect the length of offshore stay period. So this is the usually, if I were offshore operator, I work 3 months, 4 months in offshore installation, and I have a kind of holidays for 8 months out of the offshore installation. But the 8 months is for kind of compensation for working in offshore installation. So what I mean is that the length of offshore stay period, if you consider the length of offshore stay period, that can distort the actual risk that I may have. So I prepared this. It can, my expression can be confusing. So individual risk, we have a PLL. Okay, PLL is very simple. In this platform, for 10 years, we have 12 fatalities. So PLL is a very straightforward quantity. FAL is PLL times 10 to 8. This is a kind of normalized quantity divided by exposed hours. So it is POB is persons on board. It's the number of crews, in short. POB times the hours per year, number of hours per year. So we can calculate the value very straightforward. So in estimating PAR, we don't distinguish. We assume that the older people here are exposed to risk, even though they spend 2/3 of their times in living quarters. Living quarters is relatively safe. We can say that, okay. Living quarter usually is protected by firewall or explosion wall. There are process and utility areas here. So this area is kind of plant area. Living quarter is a relatively safe area, but can we say that the people in living quarter are completely safe as the people in onshore? Here is onshore. Okay? Compare the people here and here. If there is a big accident, like fire and explosion or ship collision, this guy or girl may have higher risk than these people. So we should not assume that the people in the living quarter out of their shift are safe. So exposed hour is just POB times the number of hours per year is the correct value for exposed hours. 이해하시겠어요? 그렇죠? 이해되나? AIR is the PLL times exposed individuals. So PAL POB times this hour divided by H. H is the offshore hours per person per year. So if usually I spend four months per year in offshore installation, so this should be considered here. Okay. Anyway, the detailed explanation is available in the text, and there are some examples to calculate FAR, AIR, and those kind of things. So you should solve the examples and understand the examples. So this is a kind of AIR. The FAR is not affected by the shift, okay, but AIR is affected by the shift because this is the offshore hours per person per year. What I mean is that, okay, this is a kind of apparent risk. This is a kind of frequency of fatality for this FPSO. I can spend here 1 month. For example, I'm a maintenance engineer of compressor. So I'm usually out of the FPSO. So if the compressor get failed, I visit the FPSO. So I spend 1 month maintenance engineer. I'm a process engineer. I need to monitor the process all the time. So I should be always in the FPSO. But so my contract is that I need to spend 4 months in the FPSO. For the last 8 months, I stay out of the installation. Then, which has the higher risk? Yeah, because process engineer spend 4 more times than the maintenance engineer. So we can say, so we need to consider the time spent in the offshore installation. So what I mean is that individual risk depends on the time spent on the installation. It's a very simple concept, okay? It's not a big thing. It's just a definition. So you should not be confused with the terms. FAR1 usually means so as you know, FAR, and in order to convert FAR to individual risk, we should know the POB and the AIR, individual risk, can be converted to FAR only if we know H. So typically, H is 4 months. Okay, usually I spend 2 weeks in offshore installations and take 4 months off. Considering that contract, FAR1 means just 10 to minus 4 per year individual risk. So this is kind of sense of magnitude of FAR. So the typically 10 to minus 3 per year is a limit of acceptable fatality risk. So we can say that FAR about 10 is a typical value for the offshore installations. So please check the example. And another thing, so in summary, individual risk, and let's compare PLL and IR. Both are about the fatality within the installation. So there arises another necessity on the impact on society. So impact on society is usually expressed by group risk. So this is the original intention to develop this concept. But unfortunately, there is a widespread confusion between the people in this area. So originally, this concept, group risk, is developed for the fatality of the society and the people around the facility. So you should not get confused with the fatality risk of different group of engineers. So what I mean is that the control engineer usually stay in the control room, and their IR maybe much smaller than the IL for the field maintenance engineers. So there are different group of engineers, but so usually some people use the group risk to distinguish the different levels of IL for the different groups of engineers. But this is not the original intention to develop the concept of group risk. Group risk is the risk for the people, non-operators, the people around the facilities. So this concept is effective when the extent from the installation may cause fatalities of the society. For example, fatality of a gas leak for a chemical plant. There is a chemical plant and there is a big gas leak and many people can be died. So we can estimate the risk of the people around the chemical plant. So we use the term group risk for the societal risk of the concerning the leak from the chemical plant. Anyway, FN curve is group risk is expressed by FN curve. So, but I think this is the cause of confusion. FN curve is very effective to show the overall trend of the risk. So FN curve can be used to express the individual risk. Okay, so FN curve can be used for group risk and the risk for individuals, the individual risk. So many people get confused that group risk is the risk for different groups of engineers, but it was not the original intention. But anyway, original intention is not important. The important thing is the how convenient the concept in expressing the risk. This is the FN curve. You should understand this graph very carefully. This is the frequency. So frequency is not confusing, but you should be careful about this axis, x-axis. X-axis is fatality, but this fatality is not the individual fatality. It is this is a cumulative fatality. What is the cumulative fatality? Let's see this graph. This is the FN curve, and we can read like this: 1,000 people. Here's 100. 100 here, and the frequency is 1, 2, 3, 4. 4 times 10 to minus 4 per year. So when you interpret this, you should interpret like this: the frequency for 100 or more fatality is 4 times 10 to minus 4 per year. I know how confusing it is, but actually it is a very convenient concept. So I prepared an example. There are many accidents, and I rearrange the accident along the number of fatality. In this table, one people died for an accident, and the frequency of that accident is F1. There are another accident, 2 people can be killed, the number frequency is F2. So we may have this kind of information easily, okay? So we can draw a graph for this accident. So the first trial is that we show the information on the graph. This is F and this is N. It's number of fatality. Then there's 1, 2, 3, 4, 5 like this. Okay, this is the fatality. And we can have a graph like this. Okay, maybe the accident causing 4, 5, or 100 has lower frequency than the accident than with 1 fatality. So typically, the graph is like that. The frequency for the accident with 100 fatality is very small, and this would be big. The frequency for the accident causing 1 fatality may be high. So this is the typical shape, typical trend like this. Do you agree? 100사람이 죽을 사고는 확률이 낮고 프리퀀시가 낮고 한 사람이 죽을 사고의 프리퀀시가 높겠죠. But this is just over trend. If we draw a line, this is the high, the frequency that can cause 2 fatalities can be low, but there can be no frequency for the accident that can cause 3 fatalities. There can be, what I mean the possibility. 3사람이 죽을 사고가 꼭 일어나라는 법은 없죠. There's no absolute guarantee that there should be an accident that causes 3 fatalities. So it may be like this. Like this. So the graph, if you draw a graph, it's very erratic. The graph has a very erratic shape. We can see the overall picture of the distribution of the accident. So we are thinking about the cumulative frequency. So that's why we think about the cumulative frequency. In this graph, in this concept, we start from the largest extent. Largest extent have a small frequency of occurrence. Then Fn is just Fn, large Fn. The F small, lowercase Fn minus 1 is equal to Fn times Fn. Fn is like this. So we add the frequency from the biggest extent. Then, what is the meaning of this one? This one is just frequency of the accident that cause 2 fatalities. What is the meaning of this? The frequency of the accident that caused 2 fatalities and more. So let's return to the original graph. So this point means that the frequency 4 times 10 to minus 4 is the frequency of fatality of 100 and more. This concept is not new to you. Okay? When you deal with probability, there are 2 kinds of concepts. One is probability density function, and another one is probability function. Let's do a kind of experiment in this room. Here we have a frequency. Here we have weight of our body. I think it looks Alien is the lightest. So we may start here. For example, 45. Too much? Anyway, so we have 1 person here. 50, we have 3. Maybe 55. There's no one here. I am around 90. It is surprising. Actually, my weight is more than 90. So 1. So if we draw a line, the frequency looks like this. I think only one guy is more than 90, like this. Okay, this is the weighted distribution of this class. What is this? This is a kind of probability density function. So it is very hard for us to have a kind of overall picture of weighted distribution. So alternative way is we add the frequency from here. Then the curve is here we have weight, but this frequency is a cumulative frequency. 1, then there are 2, so the value is 3. There is no one here, like this. So overall trend is upward, but the graph is more smooth. This kind of concept is always frequently applied in many areas. If you learn about chemical engineering, you may have experience to estimate the reaction rate. There are 2 kinds of method. One is to measure the instant rate. Another approach is the integral way. The simple method is we can measure let's start here in desert. I drive a car to Seoul. Then in order to estimate my average velocity, I can record my speed every second. Okay? That kind of approach is a derivative approach. Another simple way is I know the distance from here to Seoul, and I know the time spent for the driving. Then we can, if I divide the whole, I'm the 180 kilometers, 2 hours, then that means it's 90 kilometers per hour. So what I mean is that this kind of integral concept is very convenient in many cases. So the graph is only the plot. What does that mean? Extent here, extent causing 1, 2, 3, 4, 5, 10. They are small frequency. If there are many frequency, the graph should be steep. So this is we can have a big picture of the fatality distribution. There's extent. So what is the maximum, biggest extent? That is 1,000, 2,000, maybe 1,500. There can be an extent that can cause 15 people can be killed at once. The frequency is 7 times 10 to minus 5. There is another frequency here, so we can estimate the difference and the change of how the extent are distributed. Impairment of major safety functions. This is the typical in order to major safety function is kind of last resort to the people, for the people to escape safely from the installation that may be subject to a big accident. So we needed to understand the evacuation procedure of the offshore installation. So let's go one by one. This is a typical procedure. There is a gas or fire. We are here. Today we have a fire on the restroom, at the restroom of 3rd floor. Did you hear the announcement? That announcement is public announcement, PA, public announcement. So before the public announcement, there are kind of detection systems that can inform Mr. Park Jong-dae to announce the public alarm. So usually there is a fire or leak, and the gas and fire detection system detects the existence of fire and gas, and there will be alarm. This alarm can be public, or this alarm can be sent to control room here. Then we do something. One may be shut down the plant because there is fire and gas. The next step is public alarm. So the public alarm is like this. There is a fire at the restroom on the third floor, so everybody should go to the safe place. So then I was at the office near the restroom, so I needed to move to a safe place. That action is called escape. So escape is moves from the site to a safe area. That safe area is called temporary refuge, TR, or sometimes mustering areas, MA. What is mustering? 대부분 군대 갔다 왔죠? 아, 남자들이 다 군대 갔다 왔네. 저만 빼고. 군대에 대해서 안 좋은 기억이 있지. 아침에 일어나면 점호하죠. 밤에 자기 전에 점호하고. 그게 영어로 머스터링입니다. 머스터링. Mustering is to check if everybody is present and okay. So display control room sometimes is a mustering place. So all crew will be here, and I am the person in charge to guarantee the safety. The person in charge is called installation manager. Installation check if everybody is here and everybody is okay. So mustering is to call attendance, and the installation manager should make a decision. What is the decision? In worst case, we should leave. If the fire is not that severe, we can send someone to fight the fire. So we can try to activate some automatic fighting system, remote fighting system. If it is not working, I can send Bistan to put out the fire. So there should be a decision. But the fire is significant, so the important thing is to survive the fire. So we make decision to leave the platform. That action is termed called evacuation. Evacuation means abandoning the installation by lifeboat. Helicopter is very convenient to escape. So they are in many action movies, escape are assisted by helicopters, but it's just a situation in movie. In your case, you should not use helicopters. Helicopters are affected by the flue gas or the gas by the fire. So it's very dangerous to use helicopters. So the first choice is boat. But unfortunately, the boat is not that comfortable. So this is a special boat, Temsk, totally enclosed, motor-propelled survival craft. So as the name implies, it's a kind of capsule, totally enclosed. So in many cases, it is a kind of free fall type. If you are working in shipyard, I think you are familiar with the free fall type. We can use the kind of crane to to make the landing smooth. But considering the situation, there was a big fire. So important thing is to survive. So free fall. Rescue is to save the crew on the sea. So this is a typical procedure of EER. E, escape, evacuation, and rescue. This is a typical procedure. There are major safety functions to help the EER. So the major safety functions are the functions that are important during EER. Escape means escape to a safe place. So the pathway to the safe area should be safe. That pathway is called escape route. So sometimes the escape route should be shielded. Okay? The shielded escape route should not be damaged by fire and explosion. TL and tasks in TL, considering the tasks, TL should be safe. There can be some fire outside the TL. If the TL is burnt by the fire, it makes no sense. So the TL should be strong enough against the fire and explosion. And sometimes we should call the onshore assistance. So the communication system should be strong to survive the fire and explosion. So communication also the one of the major safety function. Emergency control system. There should be kind of control system. The target, the role of the control system is control the situation in emergency case. So we don't mind the small things. We mind only the big things concerning the big accident. So the emergency control system is the one of the major safety functions. Considering the evacuation procedure, the lifeboat and the some facilities supporting the free fall should be strong enough, should be safe from the fire and explosion. And the most important thing is the primary structure. Okay, usually the offshore installation is 15 to 20 meters above the sea level. So if the overall structure is not strong against the fire and explosion, it is meaningless even though the TL is strong. And the escalation, there should be fire and explosion wall. These safety functions should be invulnerable to accident and needs to guarantee safe ER. So these systems should be safe. So primary structures, escape route, TR support system, human control system, evacuation system, blah, blah, blah. But there are some kind of regulations. The regulation is different from country to country. In UK, the major safety function is TL, life support, command, TL, egress, evacuation. In Norway, sheltered area is TL. Escape way, escape route, emergency control, support structure, and escalation. Preventing the escalation. So there are specific rules. They are different from each country. So the frequency of impairment What is the frequency of impairment is that the major cell function may be impaired by major extent and should be added for all possible extent. So what I mean is that if the major safety function is strong enough, we can save most people in the area. So the authority, regulating bodies, try to emphasize the strength of this safety. So their concern is how often the major safety function can be impaired or damaged by the accident. So the authority try to control the overall safety by imposing some regulations on the frequency of impairment of the major safety functions. Environmental risk. I think you're already familiar with all the environmental risk. Asset risk, yeah, that too. We have 3 or 4 more slides, but time's up. So let's cover this next Monday. Any questions? Okay, see you next Monday.